Hello, welcome back everyone. So in the last video, we started talking about phase changes and how there's discontinuity in these variables when we undergo a phase transition. And this comes from it being a mixed state, that there's some gas and some liquid, or some solid and some liquid in the solution at that point. And so in this video, we're going to really start talking about these heating curves, kind of our graphical way of showing this process and how we do these calculations, since we have to take into account the discontinuities. Okay, so enthalpy versus energy. Remember that enthalpy is a different form of energy. Both are able to figure out Q. It's just that if we're using energy, we have to have a constant volume. In enthalpy, we have to have a constant pressure. In laboratory conditions, we are more likely to be working at constant pressure. So examples of this are a beaker open to the atmosphere, or even a reaction occurring in the body, that these allow the volume to change, but not the pressure. So most of the time, we have a continuous variable, and so we can integrate to the derivative in order to obtain the change. And so we've done this many times where we say that delta H is equal to the integral of dH. But with discontinuities, we can't take this approach. Instead, we have to break the problem up into steps. And so, for example, we can go through phase 1 as a heating step. At step 2, we have a phase change. And then step 3 is another heating step. And what we can do is we can work with each of these individually and then add them up, because delta H is going to be a state function. And so it doesn't matter that we take this apart into different steps. We can still get from the beginning to the end, because the route that we take doesn't matter. Okay, so when we are dealing with heating, we are going to use the fact that delta H is equal to the integral of Cp dt. Now, it depends on if we have Cp or Cpm, whether or not we need to include the moles. And so watch your units on these. Now, when we have a phase transition, the delta H is really given by this delta H of a phase transition, and these are generally tabulated values. Okay, so let's work through an example. In this example, we're going to calculate delta H when water ice is at 263 Kelvin and it's warmed by 20 Kelvin at 1 bar. And so to start off these problems, I like to draw a diagram. And that's just so that I can really get myself organized as to what's going on. And so I'm going to start at 263 Kelvin. And for water, that means that we are ice or solid. We're going to heat until we reach 273 Kelvin. And then melting is going to begin. Once we finish melting, we are still at 273 Kelvin, and we have to heat to 283 Kelvin. And so we're going to really think about this as step 1, step 2, step 3. And so step 1, our delta H1 is going to be equal to our integral of Cp dt from 263 Kelvin to 273 Kelvin. And so we have a solid, so we have 37 joules per Kelvin mole times our delta T, which is going to be our 273 Kelvin minus 263 Kelvin, which gives us 370 joules per mole. Now, step 2 is our phase transition, and so delta H2 is going to be equal to our delta H of fusion, or 6.01 kilojoules per mole. Now, since I have step 1 in joules, I'm going to turn this into joules as well. And then step 3 works like it's another heating step. So we're starting at 273 and we're going to 283 for CPDT. And so this gives us 75 joules per Kelvin mole times 283 minus 273 Kelvin, giving us 750 joules per mole. So give myself some more space. We said that this step was 370 joules per mole. This step was 6010 joules per mole. And this step was 750 joules per mole. And so our delta H is going to be the sum of all of these, giving me 370 joules per mole plus 6010 joules per mole plus 750 joules per mole, with a sum total of 7130 joules per mole. So if you know the temperatures of the phase transitions, the specific heats, and the enthalpies of these phase transitions, it doesn't matter where we start or where we end. We can break this problem up into these same steps, where if we heat something, we use CPDT. If we phase transition, we have to use the delta H of that transition. And then we can add all of our steps together. Okay, and so these slides I'm going to walk through real quick because these are the typed out version of what I just scribbled on the screen for you. And so I broke this up into heating of the ice, melting, and then heating of, and this should say water. This should also say water. And so I use CPDT for the heating steps, and I use the enthalpy of the phase transition for the melting step. And then I added them all together. Now, there's one more property, and your book walks through how we get this property, but I'm going to just give it to you. Because it really, I mean, it's pretty basic. Remember that we've said that we've said that dq is equal to TdS, and at constant pressure, that dH is equal to dq. And so we can say that dH is equal to TdS. Or we can rearrange things and we can get that the delta S of the phase change is equal to the delta H of the phase change divided by the temperature of that phase change. Now, in our book, whenever you see this phi, this is saying that it is for a phase change. Okay. Okay, so this should help you get going on the homework and help you to start working through these phase change steps. In the next set of videos, we're going to talk about what happens if we change pressure, and we're going to start talking about how we can map the phases at different temperatures and pressures and see what exists.